mathematical operations on this complex number. Okay, in particular, when you want to convert it from one form to another, I make it a good habit to sketch it out in the complex plane. Okay, because this will decide the angles. The angles can be in 4 quadrants, right? 4 quadrants. So if X and Y are positive, then it is in the first quadrant, namely that your angle is less than 90 degrees. Okay, but if your X is negative, Y is positive, you are actually in the second quadrant, which means that your phi, right, will be greater than 90 degrees, right? Will be more than 90 degrees. Okay, if you mark it out this way, you will never get it wrong, right? Because the rest is just to determine the required variables based on the geometrical relationship. Okay, as for the other 2 quadrants, right, in these quadrants, both X is positive, Y is negative, but in these quadrants, both X and Y are negative. So from the sign of X and Y, basically, you will know which quadrant is it in. So therefore, when you do this conversion, be very careful, because if you simply press calculator, right, sometimes you may get it wrong because some calculators does not give you the appropriate function. Okay, some calculators can do that, right? Actually, there's a function called arctan2. Arctan2 can take the sign into consideration. Okay, if not, just sketch it out so as to serve as a check. Right, after that, the rest is just to determine the geometrical information. For example, given X and Y, right, you want to find Vm and phi, all right, then it's just Vm is equal to X squared plus Y squared square root. Okay, phi is just arctan2, right, of Y over X. Okay, as for the other way around, given Vn and phi, right, is even easier. You just do the projections. Vn cosine phi give you X. Vn sine phi give you Y. So therefore, this conversions actually, right, is just a geometrical relationship between all these 4 parameters. Okay, you also have to review how to do mathematical operations, namely addition, subtractions, multiplication, and revisions, right? Basically, these 4. And for addition and subtractions, right, no other way, just rectangular form, right? So make it easy. For multiplication and divisions, you can use both, right? Actually, this extended over here, you can use both. But however, right, this table says that it may be easier for you to do it in the rectangular form, because if you multiply 2 complex numbers together in rectangular form, you just multiply the modulus at the argument, right? If you divide 2 complex number in polar form, then you just divide the modulus and subtract the argument. So this is a very simple relationship. Okay, but as I showed it to you last week, right, sometimes after multiplying, suppose that you still need to add with another complex number, then you need to go back to rectangular form, right? Because after you do this, you still need to convert back in from polar to rectangular, right? This is polar, convert back into rectangular in order to add them up. So under these cases, you can think through, right? Suppose that you start with rectangular. Okay, if you start with rectangular, then you need to convert to polar, then you need to convert back into rectangular. So whether this is easier or not, right? It depends on you. If you're familiar, you think that this way is better, go ahead, right? No problem. But I've shown it to you that under these cases, right? For me, it is that I will operate directly in rectangular form, because you can multiply 2 complex number in rectangular form as well. Okay, then I will directly get rectangular form and I will add it up, right? Then I do not need to convert anything, but you need to be able to multiply and divide in rectangular form as well. So it depends on your final objective. Okay, therefore, in the sense that when you approach the problem, try to have an overview first, see far ahead, right? So as to know which is the better way. Okay, but if you have difficulty, never mind, just stick to this one, right? Then you just keep converting when required. Okay, as we have also reviewed the reactance model in phasors, right? And this is related to our S domain analysis, because in S domain, inductance SL, right? Capacitance, capacitor 1 over SC. This is called the impedance. Okay, in AC, we just substitute S equal to J omega, right? Which means that we assume only steady state analysis, okay? And only AC signals. This is 1 over SC. Okay, and I suggest that you remember this directly, but if you cannot remember, then go back to S domain, then put S equal to J omega, right? But if you remember this directly, just write it down, 1 over J omega L, S equal to J omega, 1 over SC, 1 over J omega C. Okay, and I also show it to you that 1 over J is equal to negative J, right? You simply divide by 1, which is J over J. The purpose is to make the denominator real, because J squared is equal to negative 1. Okay, therefore, this, right, 1 over J is actually equal to negative J. Okay, I suggest that you write this down directly in your phasor model. So this one and this one you need to remember. All right, sometimes if you need to multiply, right, in polar form, it's easier to put it into this, right, with a modulus argument, because J is 90 degree. Negative J is negative 90 degree, right? This is the angle, modulus omega L, 1 over omega C. So this was basically what we have reviewed, right, in the last tutorials. Right, today, just to make a remarks of the frequency response of these two energy storage element. Okay, when omega equals to 0, actually is referring to DC, right? No frequency, DC. Okay, and if you put omega equal to 0, you can see that it's consistent to what we have learned last time. Inductor behaves like a short circuit in DC, right? Which means that impedance equal to 0. So this is consistent. Okay, the only thing new is that in the case where you have high frequency, that means that you have a sine wave, right, with frequency so large that, right, you just switch many times, right, within a second. So when frequency goes to infinity, put this in, this goes to infinity, your impedance naturally goes to infinity, right? When impedance infinity is like resistance goes to infinity, no current can pass through. No current can pass through. So therefore, is this open circuit? In this case, voltage is equal to 0. V is equal to IZ, right? Just remember V is equal to IZ. Okay. And for capacitor, is the other way around, because 1 over omega, this is omega directly, this is 1 over omega, so it's the reverse. If omega is equal to 0, then you have an open circuit, which is consistent with what we have learned in DC analysis, right? For omega equal to infinity, 1 over infinity is 0. 1 over infinity is equal to 0, which means that we have a short circuit, right? So this is how your energy storage element behave, right, at the two extreme frequencies. One is no frequency, one is extremely high frequency, right? And for frequency domain analysis, we are interested in the wide range from 0 to very high frequency. So usually the frequency will be given from the source, right? This is your omega, the frequency. For this circuit, we are interested in this particular frequency. What will happen to the voltage, right? What will happen to the voltage? Okay, here there's a I0. It means that this source, right, this control source will be depending on your current flowing through the 20 ohm resistor, right? If this is 1 ampere, this will be 4 ampere flowing downward, right? If this is 2, this will be 8 ampere flowing downwards. So it depends on this value over here. Okay, here, read the questions before you start. Use nodal analysis. Method is fixed, right? Find what? Not to find node voltage, but to find this voltage, correct? So this is what we want to do. Now, firstly, because this is AC, Secondly, because this is steady state, okay, it means that you can use phasor, right? You can use phasors. So in this course, once you see AC, right, even if it's not stated steady state, just go ahead, right? Use phasor. Okay, but more accurate, right? More accurate way, as I pointed out last week, is that it must specify steady state. Okay, if you want to analyze a transient, last week I've shown you some animation, correct? You can see that before your mass spring damper system settled down as an AC response, before that it was not really AC. It looks like, but it's not really, because AC means the same maximum amplitude, the same frequency throughout. So before that, it's called a transient. Okay, if you want to analyze VT for all T, not only steady state, right? If there's no such thing, but in this course, as I said, no need to worry about that. This is just for info. If you want to study everything, then what you need to do is convert this into Laplace domain, right? And then convert this into 1 over SC, convert this into SL, and then do the same thing, but in Laplace domain. The nice thing about Laplace domain analysis is that you can get not only steady state, but including the transient. Okay, remember last week we have seen something at the beginning. Okay, that one can be captured in Laplace domain, but it cannot be captured in phasor domain. Okay, but for AC analysis, right, because what we are interested usually is the steady state. So therefore, right, it is fine. Okay. Okay, the first thing is that we have to convert these circuits into phasor circuits. Just like you convert your circuits into S-domain circuits, similar. Okay, where instead of SL, we use J omega L. Where do you get omega? From here, right? This is your omega, is equal to 1000 radian per second. And L is given as 10 milli. So therefore, omega L is 10. 1 over J omega C, omega is 1K. L is given, right? 50 times 10 to the power negative 6. So 1 over J is negative J. Right? 1 over this is 20. So therefore, you get negative J20. Right? Just press calculator. And this means that I can now convert my energy storage element, right, into phasor domain. Resistor just same, because resistor is scalar, right? Voltage and current is still proportional. Okay, so far what we have done is that we have converted our energy storage elements into phasor domain. Okay, your AC source is also the same. Now AC source, we need to set a reference. Okay, this is cosine, right? Cosine tan 3t. So my reference is cosine tan 3t. Which means that my source is in phase with my reference over here. It's in phase. It has a magnitude of 10. Okay, as I mentioned to you, phasor is a rotating vector. Rotating vector. In this case, it is rotating at 1000 radian per second. But in our analysis, we freeze it because this is a linear circuit. All the signals inside, right? That means your V0, your V1, V2, for example, your I0, are only different in phase with respect to your reference, right? With different magnitudes. Okay, which means that they are rotating all together at the same frequency. So we freeze it, right? Freeze it and analyze it, and that is the concept of phasors. But we remember that it is rotating. So in the end, we still come back, right, to this frequency and restore it back to time domain. Okay, let us look at these circuits. Okay, remember that you need to find what? V0, correct? V0. Now you have converted everything into phasors. This basically means that all the techniques that you have learned in week 1 and week 2 can now be applied, except that you're operating in complex domain, right? Which means that you need to be able to convert the complex number from one form to another so as to perform multiplications, divisions, right, subtractions and addition. Right? Because you do all these things in week 1 and week 2, but they are not complex number, right? The only thing is that now the mathematical operations are different. So you need to be familiar with that. Now this question say use nodal analysis, right? No other way. Nodal analysis to find V0. Right? We know that nodal analysis means you assign node voltage V1, V2, correct? V1, V2. Okay, but we need to find V0. Okay, which means that you need to make use of the node voltage to find V0. Right? In particular, right, you see V0 is here. So it is related to V2. Okay, in fact, this is V2. This is V2, right? As I said, always view it this way if you're confused. 0 volt, climb up, right? V2 reached this place with voltage of V2, right? And I'm on ground floor. I climb up 10 story, I reach 10th floor, right? So this is the mean. This is the potential difference. Well, this is the node voltage, right? At this point. Okay, and here you can see that V0 can be obtained from voltage division, correct? If this is called Z1, this is called Z2. Then V0 is a portion of V2 according to the ratio of the impedance Z1 divided by Z1 plus Z2. So this is my overview. Okay, as I said, before you approach the questions, try to have an overview first, right? Otherwise, you are just randomly trying to solve it, right? Which could be very confusing. Right? This is what I always do. I look at the questions carefully, use what method, find what, right? And then I will then organize this way. I'll use nodal analysis to find V1, V2, but I only need V2, right? I only need V2. I don't need V1 actually, but you need this to solve for the V2. Okay, then after I get V2, I use it to find V0 by voltage division law. But if you can write this down, it's already half done, right? The rest is just to do it carefully. Of course, you need to know what is nodal analysis. Right, let us review it. Nodal analysis is based on Kirchhoff current law, only 3 steps. First, you assign node voltages, V1, V2. So these are the unknown. In circuit analysis, actually is about solving for the unknowns, and you check how many variables are there in your equations, right? If there's only one variables, you can solve it directly. If there are 2 variables, means 2 unknown, you need 2 equations. If there are 3 unknowns, you need 3 equations. 4 unknowns, you need 4 equations. Right? And how to solve this equation? These are linear equations that you have learned in EE 2007. How to solve systems of linear equation. It's just that over here, your linear equations may not have constant coefficients, right? But the concept is the same. Okay, so you assign node voltages, then you need 2 equations, right? Because there are 2 unknown. So you go to each of the nodes, you apply Kirchhoff current law, write down 1 equation. You go to another node, apply Kirchhoff current law, you write down another equation. So the idea is to write down equation in terms of V1 and V2, right? They must be in terms of V1, V2, V1, V2. No other variables. No other variables. So here you have I0, correct? If you have I0, you must try to relate I0 to the node voltage. Right? How is it related to? You can see here very clearly that I0, right, I0 is equal to what? V1 divided by 20. Ohm's law, right? This is actually V1 because this is not voltage, right? So 0 volts. This is not voltage V1. It means the voltage across it is V1 minus 0 divided by 20 is I0. Then I0 can be expressed in terms of V1, so you can get the equation in terms of V1 and V2. And so remember, the whole idea is to write down equation in terms of the node voltages and then solve it using any method, right? Any method that you know, right? Usually, you need to know how to solve, right? At least 2 or 3. Right? More than that is very hard to solve by hand. That will be EE 2007, right? You use other methods, Gaussian elimination methods, right? And some other methods to solve it. But for this course, usually we'll limit to 2 or 3 variables at most, right? Okay, so let's start with the first step. Use nodal analysis to find V1, V2, and we start with the first step. Assign node voltages V1 and V2, and then we take Kirchhoff current law at the unknown node voltage, right? Take note that it's the unknown. That means it is known already. You need not do any Kirchhoff current law to write down the equation because it's already known. So why do you need to write down the equation, right? If the node voltage is known, then the answer is already given. Okay, use nodal analysis to find V2. I will do KCL at node 1, which is this node, right? Inflow. Okay, this is 10, right? In phasor form because this is 0 volt. So 10 minus V1. Voltage across 20 ohm resistor divided by 20 is Ohm's law, give you the current flowing into the node. Okay, there's a current flowing out from here, 20 ohms. This is actually your I0, right? But I want to express in terms of the node voltages, only these two. So I see I0 is what? V1 divided by 20, V1 divided by 20. Okay, next, I assume outflow, V1 minus V2, V1 minus V2 divided by negative J20, right? Is this current flowing through the capacitor. So I write down one equation. Look at the equation, only V1 and V2. Okay, the rest is just to arrange it properly, right? So that you get something like this, right? So you have to know what you are trying to get first. I want to get the equation with V1, V2 equal to something, correct? This is the linear equation, except that you have complex coefficient. Okay, the rest are the details. Let us go through. Okay, I do not like to deal with fractions, so I multiply by 20 on both sides. Right? If you multiply by one side, you need to multiply by the other side. Why 20? So as to cancel out all this, right? Cancel all this, then you end up with this. Okay, you can also multiply by 20j, up to you. Then this will cancel out this one as well, but the j will appear here, right? J will appear here. So the whole idea is that you will like to get something like that, right? So it's up to you. Maybe 20j is better, you can try. Then you no need to do this inversion. I suppose I multiply by 20. Then I will get this 10 minus V1, no more 20, V1 plus V1 minus negative J. Okay, remember I told you, right? Just remember 1 over J. 1 over J is negative J, right? 1 over J only, right? No real part, only imaginary part. 1 over J is negative J, so 1 over negative J therefore become positive J. So I have a positive J here, which means I bring this to the front, right, to the numerator. Okay. And then after that, I bring V1 over here. I get 2V1. Then I group V1 together, right? I get 2 plus J. And V2 only one term, right? There's negative sign, so I get negative J, V2. So this is the equation that I want. This is one equation with two unknowns. The only thing is that you have complex coefficient. Right? If you want to compare with your linear system equations, right, you can call this K1, K2. K1 is a complex number, K2 is also a complex number, that's all. Right? The rest is the same, you can use the same technique. So I've taken KCL at node 1, I get one equation, but I have two unknowns, so I cannot stop here. Okay? That means that I need to go on to the next node to get another equation. Okay, if I take KCL at node 2, right, then I can write down 3 currents, 1, 2, 3. Right? Inflow equal to outflow. Inflow is the same, V1 minus V2 divided by this. Right? So actually you need not waste time, just use the same sign. Right? Just now you have this one, correct? Use the same direction, and then you copy it down over here. Right? Copy it down over here, so that no need to waste time. Just focus on these two. Outflow is 4I0, right? 4I0. But if you put 4I0 here, then you have a problem because you have one more unknown, correct? So the whole idea is that I want to relate it to V1 and V2 only. So I track where is I0. I0 is here. I0 is related to V1 only. V1 divided by 20 Ohm's law. Right? Voltage V1 minus 0 divided by 20 is just Ohm's law. Therefore, I express for I0 in terms of V1, and then I move on to the last one. Okay, this is V2, this is 0 volt. So V2 minus 0, and then the impedance across it, this is in series, so you add them up. 30 plus J10, right? 30 plus J10 is the series combination impedance. So I get another equation. Okay? And I need to simplify this equations. Okay? And over here, I'll start with this one. I'll start with this one. Now you can see over here that of course you can use polar form, convert, right, to 1 over this. You can convert using polar form, but in the end you still need to add. Alright, you still need to add. So I will do directly in rectangular form. This is what I've shown you last week. So the whole idea is that if you want to make this into a complex number should have a real part and imaginary part. 1 over this is not in a rectangular form, right? You cannot get a real part and imaginary part because there's 1 over this. If this is in rectangular form, this is not in rectangular form yet, right? This is rectangular form, but 1 over this complex number is not in rectangular form. I convert it by making my denominator real. How do I do that? I know that if I multiply the complex number by its complex conjugate, that means reverse the sign of your imaginary part, then you'll get real. 30 square plus 10 square, right? And if you multiply the denominator by the complex conjugate, you also need to multiply the numerator by the complex conjugate, because this means that I multiply by 1, no change. Okay, if not, then you're changing your complex number, it's wrong. Okay, after that, it just means that you reverse the sign of your complex number and then divide by the square of the modulus, x squared plus y squared, right? No square root. So it's 30 square plus 10 square, and this is your real part now, and this is your imaginary part. Okay? This is your imaginary part. So I get this converted into a rectangular form. Okay? Rectangular form. Then I, simplifying it, group all the V1, V2 together, right? You need to add and subtract, that's why I remain it in rectangular form. And then I can get this equation. Okay, next, these equations, right, only have V1, V2. Only V1, V2 is different from the previous one in the sense that there's a 10 here, right? The second one has only V1, V2. Right? Some equation may end up this way because everything is just directly V1, V2. Right? There's no constant terms or complex terms. They will end up with some other coefficients. Now here you need to make a decision, correct? Whether you express V1 in terms of V2 or V2 in terms of V1. So you go back to your formulation, right? Write down the formula. I want to find V2. I do not need to find V1, correct? Which means what? You should express V1 in terms of V2. You express V1 in terms of V2 so that I can substitute V1, right, by V2. I can substitute V1 by V2. Okay, then I solve for V2, right? We'll see that later on. So just express V1 in terms of V2 because I want to solve V2. Okay, and you can either put it in this form and continue, or if you would like to simplify further, right? 3 divided by 5 is 0.6. Right? 4 divided by 5 is 0.8. Okay? So either go ahead with this or this. Okay? It doesn't matter actually because they are the same. So I have obtained 2 equations with 2 unknown, and I know that I want to solve for V2 only so as to find V0. So this is what we have done so far. Okay, we want to find we want to use nodal analysis to find V1, V2, right? And we assign node voltages V1, V2. We take KCL at node 1, we write down equation 1. We take KCL at node 2, we write down equation 2. Okay, if there are any variable not in terms of V1, V2, relate it to the node voltages, because you only want the equations with V1 and V2 only, then you solve the equations, right? Using any methods that you know. Right? Usually for two equations with two unknowns, substitution method is the easiest. Just express one in terms of the others and substitute, right, into the other equation. Then this will be replaced by V2, right? Then you see your equation only has V2 because you substitute one variable by the other variable, right? Therefore, there's only V2 because we want to solve for V2. If you want to solve for V1, then do the other way around, right? But here we want to solve for V2. Okay, the rest is to do it carefully. I will take out my V2. Right, this is what I get. Therefore, here I get a negative J, right? And then here, I just operate directly in rectangular form by multiplying, right? Actually, you multiply this, all right? You need to multiply this 4 times. This 2, this 2. So altogether, multiply 4 times. 2 times 0.6 is 1.2, all right? And J squared is equal to negative 1. So this multiply this give you negative 1 times 0.8, okay, which is what? 0.4. So actually multiplying in rectangular form is not that difficult. It's just got to be careful, right? But if you convert it into polar form, right, there's also need to be careful of the conversion error. Okay, so I multiply these two to get a real part. Then I multiply the other two. This multiplied by this, correct? You get what? J 0.6. Okay. But I also need to multiply this with this. This multiplied with this. I get another J 1.6. So altogether 2.2. Right? 2.2. So here I operate it directly. Right? Operate directly because here I have another subtraction. Okay? I need to try to remain in rectangular form. Right, so I reproduce this one over here. Let's continue. Okay, after that I just merge these two together. Right, I get in this form, and then I'll directly get V2. Right, get V2 by bringing this to the other side of the equation, this whole thing, so that I get V2 only. And here, no need to simplify anything first. Just leave it, because my answer is not V2, right? Remember, I used nodal analysis to find V2. Now I found V2. I still need to use voltage division law to find V0. V0 is actually what I want. Okay, V0, remember, is the portions of V2 according to the ratio of the impedance Z1 divided by Z1 plus Z2, right? Z1, Z2. So therefore, the next step is to substitute this into here, right? Multiply these two together, you get V0. Okay, so this is what I do. I'll substitute this whole thing into here, right? And then I get this one. Now here, we know that finally you want to put in polar form, correct? Your phasor must be in the polar form. Okay, with a magnitude and an angle, all right? So finally we want to put into this form. So this, in this case, right, it makes sense to operate in polar form, right, because it's easier. Okay, here we have multiplication and divisions. We have multiplications and divisions over here, right? So I will convert all the complex number into polar form. For example, this one, negative 40 plus j10 is in polar form, right? Over here, this one is in polar form. Okay, this one is also in polar form. How do you do that? Square of this, square root is this, right? Arctangents of this is this. Now be careful, here is 165, right? As I told you, always mark it down, then you will never get it wrong. This negative 40 is here. This is positive 10. So actually my vector is here, right? Then the angle must be more than 90 degrees, right? In fact, you can just do it this way, find this angle. It's easier to find this angle. This angle is 10 divided by 40, correct? 10 divided by 40, then 180 minus this angle is equal to 165.96, right? So I get this one converted to this, and this converted to this, right? These are both positive, so it's actually here. So you have a small angle. Well, the other one is also over here, right? It's also first quadrant, so you have an angle less than 90 degrees. Okay? Because both x and y are positive. Now in polar form, right? Remember, polar form is easier to perform mathematical operations of multiplication and divisions. Right, so let's do it now. Right, in fact, you can just do this first. Means what? 3 times 41.231 divided by 3.162 divided by 6.356. You get 6.154. Right? That means multiply, right, and then divide. Right? Multiply and divide. Okay, for the angle, if as a numerator, right? Numerator, if a numerator you multiply, you get plus. Okay, but all these are at the denominator. So this means what? 165.96 minus 18.435 minus 77.27, right? This minus this and minus this, denominator all minus. So you get this angle. And I don't need to convert back into rectangular form anymore, right? So this, I operate in polar form. Okay, but don't worry, if you want to do it in rectangular form, then convert polar form also fine, right? No problem. It's very flexible. It's a matter of your preference and which one, right, you think would be easier for you. Any questions? So finally, right, don't forget that we have a reference of sine 3000t. This means that this signals with respect to this reference, right? This signal is rotating with respect to this rotating vectors, my reference, by angle of 70.25 degree, leading my reference by 70.25 degree, and it has a magnitude of 6.154. Okay? So actually this phasor represents AC signals, right? Just remember that. It's just that we perform the mathematical analysis in the complex domain. And then take the real parts, right? You'll get back your actual signals. Any questions? Any questions before I move on? Right, so this tutorial is good in the sense that, right, we get to review all the important methods, nodal analysis just now, mesh analysis right now. All right, so the method is specified. You need not think about it, but actually we can also make a decision if the method is not specified, right? It's quite clear. Over here, we know that we have 3 meshes, 1, 2, and 3, all right? Now, if you count the nodes, 1, 2, 3, 4. Correct? 1, 2, 3, 4. All right, this one is a node. There are two components connected together, but if you know this voltage, then this is just V plus 24. So it doesn't introduce any unknown, right? Because this is known. So 4 nodes, 3 meshes, correct? 4 nodes, 3 meshes. Okay, the choice is clear, and there's something even better. This current is known, right? If you call this I1, it means what? This is your I1. I1 is given. So the answer is already given, right? Don't go and take Kirchhoff voltage law around this loop. You get nothing because the answer is there already. I1 is given. So watch out, right, for the known current. In mesh analysis, you want to find current. If current is known, is good. So same thing here. This current is known already. All right. So if you assign this as your right I or I2 or I3, doesn't matter. It depends on the numbering. Let me check. Right, so be consistent. Let's say this is I3. Okay. Actually, you can see this current flow in this direction. And normally you just assign all clockwise, correct? All clockwise. But actually you can assign the other way around, anti-clockwise. It doesn't matter actually. Okay, if I assign anti-clockwise, then I3 is equal to 4, because this is your I3. But if you assign clockwise, never mind, I3 is equal to negative, right? The other way around, negative 4. So the answer is also given. Answer is also given. That means that there's only one unknown. Only one unknown. Now, look at it. One unknown as compared to 4 unknowns, right? 4 unknowns, 4 node voltages. So which one is better? Mesh analysis is better, correct? So this is how we make a quick decision sometimes. Just count the number of unknowns. Bear in mind that some are the known, right? Variable, like this one, this voltage is known. So you shouldn't count this as unknown volts, right? This is just V plus 24. So there are 5 nodes, but 5 nodes, but 4 unknown voltages. Okay, there are 3 meshes, but only 1 unknown current, right? So this is the circuits that we are dealing with. Okay, and the other thing to take note is that there are multiple sources. 1, 2, 3. All right. Okay, we must assume that they have the same frequency. Right? It must be the same frequency. Otherwise you need to use this one, principle of superposition, to solve it. Right? Principle of superposition is actually it means this. Okay, deal with one source at a time. Okay, if start with this source 1, for example, kill the other 2. Kill the other 2. Then find V0, right? Find V0. Now, then move on to the other source, say this one, right? Kill the other 2. This one open, this one open. Then find V0. Right? Finally, move to this source, kill the other 2, short this one, open this one, find V0. Okay, that means that you are doing analysis on 3 different circuits with 1 source at a time, right? 1 source. Why I said different? Because once you remove one of the source, it's a completely different circuit. This is the principle of superposition. When they have different frequency, it doesn't mean you cannot solve. But in this course, we are focusing on same frequency, same omega, same omega, same omega, right? If you have omega 1, omega 2, omega 3, then it's different. Use superpositions theorems, right? That means that only look at one at a time and then add them up finally, superimpose them together finally. Right, just take note of this, in this course, as I said, we have to assume that they have the same frequency. If there are different frequency, it means what? Your phasor are rotating at different frequencies, so it will not maintain the same phase difference, right? Imagine one guy run faster than you can't maintain the same distance, right? So this is the same idea, in the sense that we will not be able to write down those, right, phasor analysis, because it's based on the assumptions that the same phase angle is always maintained. Remember, they are rotating, right? They are not stationary, but we freeze it to analyze it. Okay, and we have to assume that they are the same frequency for this question, right? And here we need to use mesh analysis to find what? Use mesh analysis to find V0. Okay. Even though this voltage, but never mind. Once you find the current, you can find voltage, because why? Voltage is impedance times current. Now this current flowing through here is this is I1, right? Remember this I1. I1 is known. I1 is this one, right? Given. I1 is known. Answer given, right? And then next one, I3 is also known. I3 is this one. This is your I3. I3 is -4, right? -4, 0 is -4. So it's also given. The only unknown is I2, right? So this known, remember that. Okay, if I1 is known, right, then I only need to find I2. In order to find the current flowing through the 2 ohm resistor, right? Because this is I2. Right? When you assign this means this is I2. Right? When you assign this way, this means this is I1. When you assign this way, this means this is I3. So KCL at this node, I1 inflow is equal to outflow, right? I2 plus I is the current that I want to find out. So I is equal to I1 minus I2, correct? I is equal to I1 minus I2, Ohm's law, I times 2, V0. So this is my overview. I need to find V0. In order to find V0, I need to find I2, because I1 is already known, right? And to find I2, I'm asked to use mesh analysis. Okay, which means that I will only find I2. Now, take note, there's only one unknown. How many equations do you need to solve for one unknown? Only one equation, correct? Only one equation is required. Okay, this basically means that I don't need to take KVL at this mesh. I don't need to take KVL at this mesh. I only take KVL at this mesh. Because I only need one equation to solve for only one unknown, right? Only one. So if you go back to review your my summary again for all these basic circuits laws, right? Actually, it's very specific. It says that assign mesh currents, right, and then try to see whether some of the current is known or not. In this case, I1, I2, I1, I3 are known, so the only unknown is I2, correct? I2. Therefore, you only apply KVL at the unknown mesh, right? At the mesh with the unknown current. Okay, if there's only one unknown, then you need only one equation. If there are two, then you apply at the two meshes. Then you solve, correct? Then you solve for the unknown mesh currents. So over here, okay, we know that this is known. This is known, which means that no need take KVL here. Just take KVL here. Write down one equation, then solve for this one equation directly. All right, so this is what we will do. Right, because these two are known. Any questions? Right, so I repeat it again because I1 and I3 are known, right, given. Therefore, there's only one unknown in these circuits. So therefore, we take KVL at this mesh to solve for I2. Right, so this is what we'll do now. Ignore this 2 because answer already given, right? Answer already given, no need to do anything. Take KVL only at mesh 2, this mesh. Okay, we write down one equation because one is sufficient to solve for one unknown. Okay, when you write down these equations, right, if for example starting from here, and over here Ohm's law, 2 times I2 minus I1, right? I2 minus I1, that means that you go this way. So this I2, I1 is the other way around. I2 minus I1, then you reach this one, J3, negative J3. There's only I2 here, right? Only I2. And then here we have 24 volts. Okay, and then finally we have this one, 2, right? Current flowing through here, be careful. I2 and the other way around, right? I3. So I3 is the other way around, it's against this loop. So I2 minus I3. Then we come back to 0, right? So even though this equation contains, right, I1, I2, I3, but however, I1 is already known, I3 is already known. So effectively, right, there's only one unknown, right, because this is already known. So either you directly substitute into the first equation and proceed, or you may want to group them as I1, I2, I3 first, then substitute, right? It's the same thing. Either you simplify, then substitute, or substitute, then simplify, right? It's the same thing. We can then, right, proceed to solve this equation. Okay? Solve this equation, that means that over here, substitute I3 equal to negative 4 into here, substitute I1 equal to J8 into here, then there's only one unknown, and then we can solve for this I2, right? So the remaining step is to do this. Substitute I1 by J8. Substitute I3 by negative 4, right? And then you get the next equation. Then there's only I2. If there's only one unknown, you only need one equation, and you can solve it by what? Algebraic manipulation, right? Just bring this to the other side of the equation. Okay, this you get 32, bring it to the other side, you get negative 32. This negative 16J, bring it to the other side, you get positive 16J, right? And divide by this, you get I2. Okay, after this one, right? I2. Now, take note, I2, go back again. Our overview. I want to find I2, then I need to subtract I1 with I2. So therefore, subtraction, correct? Subtraction, you need rectangular form. So go back this one. Right? I finally need to do subtraction. So I need a rectangular form. Alright? I need a rectangular form. Okay, therefore I need to convert this into rectangular form. Because later on I still need to do subtraction. Right? So bear that in mind, then you may not waste unnecessary time, right? So I have this one. I want to convert into rectangular form. Any way you like, right? You can convert polar, then polar, rectangular, or you directly perform multiplication. Okay, also can. Okay, that means for this case, actually you can multiply this by the complex conjugate. Then the denominator will become real, and then you multiply this complex number with this complex number, right? You'll get this one. As I said, it's a method of fraction, but you must be familiar, right, with both method, or at least one of the method, right? So I put it in rectangular form because I know that I need to do this subtraction later on. In subtractions, addition, no other form. So far what we've done is this. We use mesh analysis to find I2. Why only I2? Because this is already known. This is already known. The only unknown is I2. And after we found I2, we use it to find V0. Right? Use it to find V0 because current voltage are just related by impedance law or Ohm's law, right? Impedance law or Ohm's law, V is equal to IZ. So that means that if you find one of them, you can find the other. This also means that if you know all this current, actually you can go back to find all the node voltages if you want. Okay, you can go back to find all the node voltages of these circuits. So we have found I2. Now I1 is also known. It's already in rectangular form, right? We have converted it, and therefore we can do the subtraction. Right? If you subtract this, I1 minus I2, I1 minus this one. Right? It means J8 minus this one. So here negative become positive. Right? And then this is also become positive. Negative, negative become positive. So you add 8 plus 1.28 is 9.28. Right? And don't forget to multiply by 2. And you get this form. Finally, we need to put into polar form. Right? Phasor finally is polar form. That means that you have a sine wave with a reference which is not given, so just leave it. Right? If the reference is given, you need to convert back 23.3, for example, cosine omega t plus 52.82. Okay. The real parts of this. Any questions? Any questions? Okay, if not, let's move on. Okay, you can see that we are reviewing the main theorems, right? Nodal analysis, mesh analysis, and Thevenin's theorem now. So all these methods are very important, right? Because they are used to solve very complex circuits. Okay, very complex circuits. And in the case of Thevenin's theorems, okay, we try to simplify a complex circuit into a simple equivalent form, right? So this method says that use this method, Thevenin's theorems, at the terminal A, B. So there's a terminal A, B, right? Okay, that means this is your load, right? Remember, this is your load. Now this load, usually, right, when you use Thevenin's theorems, it has two meanings. One is that you simplify the analysis so that it's easier to analyze. Okay, the other one is that this load is changing quite frequently. For example, you want to find a matching load for maximum power supply. Right? There's no way that you can find it using this complex circuits. You simplify it to the equivalent form, then you analyze the equivalent, the simplified circuits. You know the load conditions in order to have maximum power, right? Or in this case, right, maybe this load is changing quite frequently. Sometimes 2 ohms, sometimes 3 ohms, right? Maybe sometimes replaced by capacitor, sometimes replaced by inductor. So it makes sense to simplify the fixed part into simple circuits so that it's easier to analyze, right? So this is what we mean by Thevenin's equivalent. We want to simplify this thing into a Thevenin's equivalent so that once you connect back the load, it's very easy to analyze, right? We shall see later on. So firstly, we need to convert it into phasor. This is AC, steady state. Cosine 1t means what? Frequency equal to 1. Cosine 1t. Simply cosine t. Frequency is 1. Use this frequency to convert your energy storage element, J omega L, L equal to 2, is J2. 1 over 4, right? 1 over 1 over 4 is 4. 1 over j is negative j. Right? 1 over 8 is 8. 1 over j is negative j. So we put these circuits into phasor form. Right? Take note that you have converted everything into its phasor form, including your source. Don't forget your source. 20 reference cosine, leading my reference by 30, so is 2030. Right? 2030. Now this is my phasor circuits. Once you convert things into phasor form, then whatever that you have learned in week 1 and week 2 can now be applied, right? We have seen mesh analysis, we have seen nodal analysis, now we will see Thevenin's theorem. So this is my overview. I want to convert these circuits, this complex one, into its equivalent form with respect to this terminal. Okay, then after that, look at this simplified circuits. It's very easy to find V0. V0 can be found by voltage division law. V0 is a portion of VTH according to the ratio of the impedance, 2 divided by 2 plus ZTH. Okay, and imagine now I say that I change this load to 5 ohms. You just change here only, 2 change to 5, 2 change to 5, then you can get your V0, right? Without having to go back to analyze these complex circuits, maybe nodal analysis, mesh analysis, or whatever. You only do it once and for all. So this is the advantage, right? And we can also find the maximum power transfer easily by using Thevenin's theorem, right? If you see maximum power transfer, it means Thevenin's, right? No other way, just use Thevenin's. So let us review Thevenin's theorems. Thevenin's theorem says that if you have complex circuits, right, you can simplify into its equivalent form. That means that you need to find two things, VTH and RTH. Okay, and then you should read my summary. It should use everything. To find VTH, actually, you must first remove the load. Right, as in this circuit, you must remove this load. Remove it. Then the remaining circuit without that load is a new circuit, right? It's a new circuit. Once something changes, it's a new circuit. You should find the open circuit voltage across this terminal after removing the load, and that is actually your VTH. Right? That is actually your VTH. Okay, you can actually see from here, if this is open, right? Is this open? Then there's no current. Current equal to 0. Okay, if there's no current, then this voltage is equal to 0 as well, correct? Ohm's law, I times Z 0. Then this voltage is actually VTH. Your VOC is therefore equal to VTH. So which means that if I have this circuit, I remove the loads, I calculate, right? Calculate this VOC is my VTH. Now in experiment, you just use a voltmeter to measure it, that's all. But this is circuit analysis, so we analyze the circuits to find VTH. So the only difference is now your circuit is in phasor forms, right? You need to use phasor analysis. Okay, that's all. The rest is the same. Now to find ZTH, same thing, remove the load first. Then look into this terminal and determine the equivalent impedance. That means that you want to represent these circuits by one equivalent impedance only, right? One equivalent impedance, and you must kill the independent source, right? So for circuits with only independent source, it's very easy because there will be only components. For resistor, just simplify the resistors. For energy storage element frequency domain analysis, you simplify the impedance, right? Reactance, using a complex number. Now take note, I see many students like to convert Y delta Y directly. Once they see something that looks like Y delta, they convert, but no need, right? Because you should always start with the simplest one, series parallel. If they can simplify series parallel, simplify only if you cannot simplify further because they are neither series or parallel, then you use Y delta, right? Okay, but however, if they are dependent sources, right? If they are dependent sources, then you cannot use series parallel. Why? Because they are dependent sources with impedance or resistance. Okay, and you cannot remove the dependent sources. You're changing the circuit if you do so, because this components contains impedance or resistance, right? So you can't do that. So the other idea is that we know that impedance is just, according to Ohm's law, voltage divided by current. Right, so this means that if you pump in a known voltage, then you determine your current. Right, in experiment you measure, in circuit analysis you analyze the circuits. So if you know voltage, if you can calculate current, then of course you can calculate impedance, right? So this is useful when you have dependent sources. Okay? Dependent sources, because why? Dependent sources contains impedance, but I do not know the impedance. Okay, once you do not know something, you test, right? Test it. Like I always use these examples. If your pipe is choked, if you want to know how serious is it, of course you have to pump in something, right? Pump in something with known pressure, then you measure the flow rate, then you know how serious is it. So this is the same thing. Put in a potential difference so that the current can flow, then you see how much current can flow, right? The lesser the current flow, the higher the resistance or impedance, right? If you flow very fast, it means not so bad. If you flow very slow, the current, then it means very, very bad, right? So this is what we will do now. We need to find CTH for this circuit. First thing that you need to do is to remove the load, right? Remember, you must remove the load first. Then look at the circuits, the dependent source. I do not know my impedance. So of course I can't simplify it, correct? And I cannot kill this because it contains some resistance. I can only kill the independent source, right? So this is a voltage source. I kill it by setting the independent source to 0. So this is how I remember voltage equal to 0, short circuits, right? Short circuits, no impedance, V is equal to IR, R equal to 0, voltage equal to 0. Okay, then I look into this terminal, right? Look into this terminal, I want to get my equivalent impedance, but I have this dependent source here. I can't use series parallel to simplify because of this guy, right? If there's no such thing here, just use series parallel, you can simplify it. But there's this guy here, so I have no choice but to apply a known potential difference, and then I see how much current can flow. From there, I can therefore get my impedance, which is voltage divided by current. Voltage is 1, so 1 divided by current. Right, you can also try 2 volts, 10 volts, 100 volts, right? No difference actually. Okay, because these are linear circuits. If your voltage increase, your current will increase proportionally, right? So when you divide them, you will cancel out. The proportional part will cancel out. That means if you get 1 volt, right? If this is 1 ampere, if you 10 volt, it will be 10 ampere, right? Just for example. Okay, then after that, what you need to do is to use applied circuit analysis to find Ix, right? To find Ix. Now, notice that here, right, you apply 1 volt here. So therefore, this node voltage is known, 1 volt, correct? Because this is 0 volts. 0, climb up 1 story, you have the first floor. So this is 1 volt. Okay. Now this is important because why? You are free to use any method over here, right? So the step is like that. You apply a known voltage, Then you use circuit analysis to find this, and using any method. Okay, then you have to recall what method should you use. Right, typically mesh analysis, nodal analysis are good for circuits with multiple sources, including dependent source. Okay, if there's only one source, right, actually you can use series parallel easily, current division, voltage division to simplify it, right? Okay, as in the quiz, you can see the first question, only one source, so you can easily use voltage division, current divisions, any methods to find it out. But you have multiple sources, then mesh analysis, nodal analysis are the two choices. So which one to choose? Check. I have only one unknown node voltage, only one. Because this is node. My answer already given, don't go and put this as V2. Even you put V2, V2 is equal to 1, right? You must write V2 is equal to 1. So only one unknown, only one. Okay, if you use mesh analysis, 1, 2, 3, correct? 1, 2, 3. Okay, and this is not considered because once you can calculate this I0, then you know this one. Right? So either 2 or 3, but 1 is still better, correct? So I should use nodal analysis. Okay? It will save you a lot of time if you spend a little bit of time to decide, right? So I only need to take KCL at this node. I can find Vx, but what I want is Ix, right? What I want is Ix. So if you feel that, right, it's tedious, right, after I find Vx, I still need to find Ix, then go ahead and use mesh analysis if you wish, right? It's also possible. But here I'll use nodal analysis to find Vx, then I'll relate to Ix by taking Kirchhoff current law at this node. Okay, because once you know the node voltage, you can know all the current relating to this node, right? And then I will be able to find the only unknown here, right? Let's look at it later on. So I'll now use mesh nodal analysis. Okay, there's only one unknown node voltage here, which means that I only need to take Kirchhoff current law at the unknown node, only one node. Because one unknown, I only need one equation, right? And then I'll solve it directly for Vx. So this is what I'll do. This is Vx, right? And this is known. Okay, this is 1 volt. So I need not do anything here. Okay, taking Kirchhoff current law at node 1, okay, I can write down 4 currents. Okay, you can assign in any directions. This one I'll just use the same direction as this one. So this is my outflow, right? Outflow. And then I will put an inflow this way, but you can also put outflow, no problem. 1 volt minus Vx, 1 volt minus Vx divided by J2, inflow, right? So I get this 2. Okay, this one I'll put outflow because usually it'll flow to ground. So V divided by J4, negative J4, right? Now this one, right, ignore this one first. Okay, because I'm only interested in the current in terms of the node voltage. So I'll put this one, Vx, outflow, right? Outflow, outflow, inflow. This inflow. These are all outflow, right? Inflow equal to outflow. So outflow is Vx divided by 4. Vx divided by 4. I don't really to worry about this one first. This one will only use when you are dealing with 3I0, right? Which is this guy. 3I0. Okay. So if it's node, the rest just try to do it in terms of node voltages, unless you can't, like this one. Okay, then let's go back to 3I0. Okay, 3I0 is not in terms of Vx. So I need to check where is I0. Right, then go back to this one. Let me clear this first. Now my 3I0 is here. I do not change the sign, right? This is by convention, it must flow this way. Flow this way. So I write it down here, I0 is this way, right? So this voltage is 0 volts connected to ground. So the voltage across the 4 ohm resistor is, because I'm flowing this way, right? So it's from 0 minus Vx divided by 4. Right? So it's 0 minus Vx divided by 4, so it's negative Vx divided by 4. Okay, that means that if you assign inflow, correct? If you assign inflow, actually no problem. What you see is that your inflow will be the other way around, will be here, and then you will be negative Vx divided by 4. Then you bring it to the other side, it's still the same, right? No difference at all. So whether you assign inflow, outflow, it doesn't matter, right? Eventually you will still get this one, and once you here we substitute this into here, correct? You substitute this into here, you get an equations with Vx only, because you have only one unknown. You only need to take KCL at the unknown nodes, express everything in terms of Vx. If not, like I0 trace back, relate to Vx, then substitute into here. You get everything in terms of Vx, then one equation with one unknown you solve by algebraic manipulation. Right, then we can get 0.4 plus J 0.8, which is my node voltage in rectangular form. Right, you can also put in polar form, it doesn't matter, but ultimately you still need to perform some more operations, right? So I leave it in rectangular form for a reason, right, which we'll see later on. Okay, next, let us look at the overview. I am in the process of finding, right, Ix. Why do I want to find Ix? I want to find Z equivalent. Okay, once I know my Ix, my Z is 1 volt divided by Ix, correct? So I have to go to do nodal analysis to find Vx, and I found Vx because there's only one unknown, so it's easier to use nodal analysis, right? For me, if you want to use mesh analysis, also fine, right? No problem. Don't worry about that. Now, if after I found Vx, right, KCL at Vx, I can get these solutions. I still need to find Ix in order to find ZTH, because Ix is here, the node voltage is here. So the next step is that I want to find Ix by using Vx, right? And then you need to take Kirchhoff current law at this node. It's not to solve the equation, but it's to find Ix, right? Because if Vx is known, then I0 is known, because I0 is Vx divided by 4. Okay, if I0 is known, 3I0 is also known. Now, if Vx is known, then this current is also known, correct? This current is actually Vx minus 1 divided by J2. So if Vx is known, then this current is obviously known. The same thing over here, this is a known current, right? This is a known current, which is 1 volt, this is 1 volt, divided by negative J8, right? So this is outflow. Now let me put this equation here first. Inflow equal to outflow, 1 divided by negative J8, right? And then I have another inflow, 3I0, right, inflow, and then I have another inflow, correct, Ix. So I put Ix here. So namely inflow, inflow, inflow equal to outflow, right? Okay, then I bring this to the other side of the equation. Basically, I get this one, Ix. I want Ix. So Ix is equal to this, right, this term plus negative of this term become 1 minus Vx plus negative 3I0. Okay? And Vx is already known, and I0 is known once Vx is known. So therefore, I can calculate Ix after I know Vx. So in a sense that once you know all the node voltages, you can calculate all the branch currents, right? And on the other hand, once you know all the mesh currents, you can also calculate all the node voltages, right? Remember that they are just related by Ohm's law. Okay, which means that now I can proceed to calculate Ix, right? Because this I0 can be expressed in terms of Vx. Vx is known. Okay, so I either simplify it first, then I substitute, or I substitute first, then I simplify. I will get the same thing, Ix. Right, this you can either rectangular form, polar forms, right, to convert then eventually to these polar forms. So actually here is maybe easier, you convert polar, 1 over polar, you directly get polar. Right? But if you want to use rectangular also can, no difference. Any questions? Okay, we have found ZTH only. We still need to find VTH, right? Still need to find VTH. Now VTH, same thing, remove the load. Then this open circuit voltage is your VTH. Okay, and you can use two methods, either mesh analysis, assign mesh current, or nodal analysis, assign node voltage. Okay, in this case, actually either way is fine. Because this one, right, once you know this current, you know this, right? So this one doesn't come into pictures because once you know this, you know this one, right? This just follow this. Okay, and basically we have two unknown currents, two unknown voltages, right? So I'll use nodal analysis because I want to find this node voltage, which is happen to be my V2. Okay. V2. So I assign node voltage V1, V2, and then I'll find V2 only. No need to waste time to find V1, just find V2. So this is my overview. Okay, let us proceed. If V1, V2 are unknown, so therefore I need to take Kirchhoff current law at node 1 and node 2. Because I have two unknown, I need two equations. Take KCL at node 1, you write down one equation, expressed in terms of V1 and V2 only, the key idea, right? So here is 220/30, this node voltage, minus V1, voltage across 4 ohm resistors, divided by 4 is the current flowing through it. This is actually your I0. Right? Because I assign inflow, so happen to be I0. Okay, then this is 3I0, so actually this 3 times of this, and then over here I have V1 minus V2 divided by J2, okay? Outflow. It is also outflow, so inflow equal to outflow, right? Lastly, outflow V1 minus 0 is V1 divided by negative J4. Okay, next is to note that, right, just now I told you this is actually my I0. Okay. In fact, maybe you should put this I0 first if you want, then bring it to the other side, you get negative 2I0, right, easier, then you substitute I0 into here. So eventually I want to replace I0 by the node voltages, right? Node voltages. So therefore I substitute this into here, I start simplifying it. To get an equation, the objective is to get equation in terms of V1, V2 only. Right, you can see that here it's possible to have complex number as well, right? Besides the complex coefficient. Okay, I have two unknowns, V1, V2. So I cannot stop here, right? I cannot stop here. I am only at node 1. So I need to move on to node 2. Take KCL at node 2. I get another equations. The whole idea is to express in terms of V1 and V2 only, right? V1 and V2 only. So this one is the same, just reproduce it from the previous one, right? Copy it down, assign same direction, and then here inflow 3I0, outflow V2 divided by negative J8, no current flowing here, open circuits, right? Open circuits. Okay, then I0, remember, can be expressed in terms of node voltage 1, right? So as I said, the whole idea is that everything must be expressed in terms of the node voltages, right? So you write down the equation first, then check which one not in terms of node voltage, then check I0 is here. I0 is related to V1, right? And then we substitute this into here, so that everything is just node 1 and node 2 voltages. Then you get another equation. Okay, so two equations is enough to solve for two unknown. All right. So if you solve it, easiest way is substitution, as I said. Okay, if you want to solve V2, right? Why you want to solve V2? V2 is your VTH. You want to solve V2, then you should use one of the equation, either one. Express V1 in terms of V2, substitute into the other equation, then there's only V2, then you solve for V2. But you can also use this one. Express V1 in terms of V2, substitute into the other equation, then you can also get V2, right? So two equation substitution methods, right, could be easier. Okay, we have obtained VTH and ZTH. Okay, but that's not the end. You want to use this to find V0, right? Then you connect back the load to your equivalent circuits and then use voltage division law to find your V0, right? V0 is portions of VTH according to the ratio of the impedance, right? 2 divided by 2 plus Z. This voltage division law. And therefore, right, we just substitute VTH, RTH that we have calculated. We can find V0. And don't forget to convert back into your sine wave, right, using cosine as a reference. Remember, cosine 1t, frequency 1, is negative, right? It's lagging behind your reference by 133.31 degree. It has a magnitude of 3.832. Any questions? Okay, so this question is rather long, correct? Okay, let me try to summarize the steps, right? The steps involved. You have this complex circuits where you want to replace everything on the left by the equivalent circuits, which means that you need to find VTH and ZTH, right? So which one to start doesn't matter, but in both cases you first need to remove the load. Okay? Once you remove the loads, then you look at the circuits. There's a dependent source, so therefore to find ZTH you cannot just simplify using a series parallel, right, combination, because there's this dependent source with unknown impedance. Therefore, we test ground by applying a known potential difference. Then we try to calculate this Ix, right? Once you know Ix, then impedance is voltage divided by current, voltage 1, current calculated, you get ZTH. Next, how to find ZTH, how to find Ix? Any method. Any methods that you wish, right? But In this case, as I explained to you, this 1 volt already known. The only unknown is Vx, so I'll use nodal analysis, but it's up to you. You want to use other method, it's also fine. Okay, once you find Ix, then take KCL at this node, because all the current are now known. If you know this voltage, you can know all the current, actually 1 volt. You can also know this current. The only unknown is this current. Then I can use KCL to find Ix, right? So basically, circuit analysis is that anything don't know, you assign an unknown variables. Then you see how many unknown, then you know how many equation you need. Right? Try to solve for the unknown based on the known one. Okay, so after that you found this, you still need to find VTH. Same thing, remove the load. Then your VOC is your VTH. That means that treat this as a new circuit, analyze this circuits to find your VOC, which is your VTH. And I'll use nodal analysis, right? But you can use any method. Okay. So this is what we have done, right? You can see that in some cases the method is not specified, right? So you're free to use any method, but choose one which is easier, right? Or easier for you. Any questions? Okay, if not, let's move on. Now, nodal equivalence can be obtained from Thevenin's by just simply source transformation, right? Source transformations. So if you want, you can also find Thevenin's, convert Thevenin's into Norton's using source transformation, but there is a direct way of finding the Norton's current, right? By short circuits, right? We'll see later on. Okay, first I want to stress that some circuits, the node is already removed. If you see this, it means that, right, previously there may be a load here, but you already remove it, right? So you don't need to remove this in this case. It's already removed, and I need to transform it into a current source in parallel with a impedance. Now, if you look at the equivalent circuit, if you short this, right, this is called short circuit current. This short circuit current is actually equal to your Norton's current. Why? Because you short it means what? Impedance equal to 0. Okay, if this impedance equal to 0, all the current will bypass this because it has impedance, right? All the current will bypass this, and all the current will come to here. So IN when come to here, none will come through here, right? Okay, actually the other way to look at it is that this voltage is 0, correct? Impedance 0, voltage equal to 0. If voltage equal to 0, if this voltage equal to 0, then no current. Voltage divided by impedance is current, no current. So all the current come through here, which means that if I short this one, I can get my Norton current, right? Because they are equivalent. So another way to find the current directly is to find this short circuit current, right? Okay, but I'll start by finding Zn first. This Zn is to first remove the load. Load is already removed, so therefore my circuit is this. Now look at this circuit, there's no dependent source, no control source. No control source means that after I set my independent source to 0, current, how do you set current equal to 0? Open. Right? When you open it, then no more current flowing through here. Right? So it looks like this. Right? And then look into this terminal A with respect to B and try to find the equivalence impedance. Okay, actually these two can be combined into one impedance, correct? Series 60 plus 40 is 100. Okay, these two can be combined into one, they are series. 50 plus negative 30 is 50. Then these two are parallel as far as terminal AB is concerned, parallel. So Z1, Z2 divided by Z1 plus Z2 give you this equivalent impedance, right? So this rectangular form, this polar form. So this is one way. Okay, if you are confused with the series parallel, right, as I mentioned to you previously before, one way is that you can connect a source here, like this A, B. So for example, 1 volt, 1 volt. Now after you connect a source there, and then everything is very clear, correct? These two are series. I can convert it into 100. These two are also series. I can combine them into J50. Right? Now, if you want to use the indirect method, that means find current, you need to find this current, correct? So that your Z is 1 over I. Now, Z is 1 over I. Okay, what is I? I is this current plus this current. Now, both of them is 1 volt. So actually, this current over here is 1 over 10, 1 over 100. Correct? Because this is 1 volt. 1 volt, apply across here, current 1 volt divided by 100. Now this is 1 volt. So 1 volt, the current here is 1 volt divided by J50. Right? And inflow equal to outflow. So actually your current I is 1 over 100. Current flowing through here. Right? Because 1 volt. And plus 1 volt divided by J50, current flowing through here. So actually you see something like this. You add out the admittance, then you invert the admittance to get back the impedance, right? It's similar. Okay, but this way, right, can be used for both method. Actually, you can see you get the same answers. But it's easier to do it this way, right? I encourage you to do it this way because this will directly simplify the circuits. But if you are not sure, right, sometimes some students are not sure why this series. Why after that is parallel, right? Actually, if you do it this way, then you can see very clearly, right? With respect to the terminal. Okay, next, I want to find the Norton's current, right? I want to find the Norton's current. So I short the terminal AB. Then my short circuit current is my Norton's current, right? So this is how we find the Norton's current. Okay, and how do you find these Norton currents? Two ways, right? Two ways. Nodal analysis and mesh analysis. Okay, nodal analysis and mesh analysis is the way to do it. Or actually, this one you may, right? You may also use some other methods, current division law or this, right? But here I'll use mesh analysis, right? Because mesh analysis is quite easy to do so, but you can actually try other methods. For example, right? This current is known, right? So then you can try to okay, here cannot, because here you want to find this current here, right, which is from this branch to this branch. Right, so we will use mesh analysis. Okay, mesh analysis says that assign mesh voltages, net mesh current 1, 2, 3, correct? At one glance it looks like you need 3 equations, but not. This is known. This means that this is a known IS is in fact given. S stands for source, IS is in fact given to you. Answer given to you. So only 2 are known, right? Only 2 are known. So mesh analysis is easier because I want to find current. right? But if you want to use nodal analysis, also no problem, right? Basically, you have one node, two nodes, right? Also two nodes. Once you find the nodes, then you have to find all the currents, then use the current to find the short circuit current, right? Right, do not merge this one because you want to find this current, right? Do not merge this. So this is what I'll do. I'll use mesh analysis to find I1 and I2. Okay, if I assign this way, this means this is my I1, this is my I2. Okay, what is this? Kirchhoff current law over here, inflow equal to outflow. IN, the short circuit current which I want to find, inflow plus I1 inflow, right, is equal to outflow. Equal to outflow. So this means what? IN, right, is equal to I2 minus I1. Okay, which means that this is my overview. I'll use mesh analysis to set up two equations with two unknowns, I1, I2. I'll solve for the two unknowns. I need both I1 and I2. Then I subtract them to find the short circuit current, which is my Norton's current. Right, so this is what we need to do. You bear in mind that this is already known, so don't go and take case VL at this node, right? No need, answer given already. Take KVL at these two nodes, okay? Only at the unknown meshes, right? Only at the node mesh with the unknown mesh currents. Okay, because only I1 and I2 are known, so I'll start by taking Kirchhoff voltage law at mesh 1. Go around this loop, right? Very simple, only two components. One of them is 60 ohm, one of them is 40 ohms. Okay, so the 40 ohm ones is 40 times I1, only I1. 61, be careful, you have IS here, right? IS, and I'm going this way. Right, so I1 minus IS. I1 minus IS, fortunately IS is known, so there's only one unknown, which is I1, right? Okay, you can also write it this way. Actually, it's the same, correct? You can see the 60 plus 40 is 100. Okay, it's the same thing, and then 60 times negative IS is negative of this. Okay, in either case, you can write down I1. You can solve for I1 directly because IS is given. Then I1 is now known, right? So I1 is now known. I take KVL at this node to solve for my remaining unknown I2. Kirchhoff voltage law around this loop. You can write down the equations again. Ohm's law, right? Is I2 only passes through negative J30. This I2. But this branch, right, be careful, it consists of IS going downwards and I2 flowing upwards. Right, I'm going this direction, so it's I2 minus IS. Right, substitute IS into here, or you can group them together first, then substitute into here. In either case, you'll get I2 equal to 4.860 degrees. So we have obtained I1 and I2. Then we need to subtract them, right? Need to subtract them to get IN, okay? To get IN. So perhaps over here, right, you can remain it as rectangular form. Then you do the subtraction. So finally, you need to convert back into polar form. Okay, polar forms. In these questions, take note that it's already phasor forms. Right, so we just leave it in the phasor form. Right, if it's initially it was in AC, then you need to convert, right, into right, it means 3, for example, cosine omega t, but this is not given, right? This is not given, so we need not do that. Because everything is directly given in phasor form already, right, for this question. Right, but just to let you know, just to remind you that this actually represents this, right? Any questions? So this tutorial, right, is quite useful because not only that you do phasor analysis, you at the same time you also review, right, the concept in part week 1 and week 2. So if you have not done this tutorial yet, right, go back and try on your own. I remember actually the guide is that you must be able to do it without referring to the solution, because you can see that if you read the solution, it's always easier. Okay, but to do it is a different thing because it requires some decision, some thinking, right? So try to do it until you do not have problems in doing by yourself, meaning that no need to refer. Then you'll be okay. Any questions? Okay, as I said, right, if you have any questions, you can always stick back to discuss, not necessarily relating to this tutorial, right? Can be your lectures or can be your preparations for examinations, right? You can always ask me, okay? Any questions? Okay, if not, never mind, right? I'll stop here today. Thank you.
Thank you, sir.
Thank you, bye.